We usually imagine the solar system as a clean, well-ordered family of planets. The sun in the center, graceful orbits, maybe a few rings and moons as decoration. Somewhere in the background, almost as an afterthought, there are asteroids and comets, the dangerous rocks that sometimes appear in disaster movies or pass by in astronomy news. It is easy to think of them as leftovers, as cosmic trash that never managed to become anything important. But that picture is upside down. Asteroids, comets, Kuiper belt objects, and countless icy planetesimals are not garbage. They are the raw, unprocessed material from which the planets themselves were built. Every mountain on Earth, every drop of water in the oceans, and a large fraction of the carbon in our bodies can be traced back to the same population of primitive objects that still orbits the sun today. They are time capsules, frozen samples of the early solar system, preserved for 4.5 billion years. When we look at a small, irregular asteroid or a dim, dusty comet nucleus, we are not looking at something unimportant. We are looking at the kind of building block that failed to become a planet, and precisely because it failed, it still remembers how everything started. In planetary science, small bodies is a technical term. It includes almost everything in the solar system that is not a full-sized planet or a large moon. Rocky asteroids in the inner solar system, icy comets that spend most of their time in the deep cold, Kuiper belt objects beyond Neptune, scattered and detached trans-Neptunian objects, and probably trillions of distant icy planetesimals in the Oort cloud. These objects are made of rock, metal, ice, and complex organic molecules. They formed from the same protoplanetary disk that gave birth to Earth and the other planets, but for various reasons they never fully merged into a large world. Because they stayed small, they avoided the intense heating and geological recycling that erased the original structure and chemistry inside planets. That makes them scientifically priceless. By studying small bodies, we can reconstruct the temperature and composition of the protoplanetary disk at different distances from the sun, test models of how dust grains grew into planetesimals and then into planets, trace the history of water and organics, including how icy bodies may have helped deliver key ingredients for life to Earth. Every asteroid spectrum, every sample return mission, every flyby of a comet's nucleus is, in a sense, a drill core taken from the first few million years of solar system history. In this episode, we are going to treat asteroids and comets not as hazards or background objects, but as the main characters, the original bricks from which everything bigger was built. To understand how these small bodies were born, we have to rewind the solar system all the way back to its beginning and follow a specific chain of events. First, we will look at the protoplanetary disk around the young sun and the idea of the snow line, the invisible boundary where water and other volatile compounds can exist as ice instead of vapor. Inside this line, only rock and metal can survive as solids. Beyond it, ice becomes a major ingredient. That simple temperature gradient is what divided the early disk into an inner rocky zone and an outer icy zone. Next, we will follow the evolution of tiny grains into planetesimals, how dust particles collide, stick, and grow, how turbulent gas and gravity concentrate them into kilometer-sized bodies. We will see why some of those bodies merged into planets, while others remained small and scattered. Then we will trace how this violent early evolution left behind distinct reservoirs of small bodies: the asteroid belt between Mars and Jupiter, the Kuiper belt and scattered disk beyond Neptune, and the distant spherical Oort cloud, the source region of many long-period comets. Finally, we will come back to the present and show why these bodies are not just relics, but active archives. Their composition, orbits, and internal structure still preserve information about the first few million years after the sun was born. By the end of this first episode, the phrase small body should no longer sound minor. You will be able to see every asteroid and every comet as a surviving fragment of the blueprint from which Earth and the other planets were assembled. In the beginning, our solar system was not a family of planets, but a cold, giant cloud of gas and dust drifting through the Milky Way. This cloud, a molecular cloud rich in hydrogen, helium, and tiny solid particles, slowly became unstable under its own gravity. Slight overdensities, regions just a little denser than their surroundings, began to collapse faster than the rest. Over millions of years, the cloud's central region contracted and heated up. At the very center of this collapse, a protostar formed, the young, not yet stable sun. It was enveloped in infalling gas, still gathering mass, still heating up toward the point where nuclear fusion would ignite in its core. But crucially, this collapse did not happen symmetrically. Because the original cloud had even a tiny amount of rotation, conservation of angular momentum forced the inflowing material to spread out into a flat, rotating structure around the protostar. That structure is the protoplanetary disk, a vast thin disk of gas and dust stretching tens to hundreds of astronomical units from the young sun. In this disk, gas dominates the mass, but dust, microscopic grains of rock and ice, dominates the opacity and acts as the seed material for all future solid bodies. Closer to the protostar, the disk is hotter and denser. Farther away, cooler and more rarefied. This disk is the workshop where planets, asteroids, and comets are assembled. The protoplanetary disk is not uniform. It is more like a giant rotating furnace with different temperature zones as you move away from the young sun. In the inner few astronomical units, intense radiation from the protostar and friction within the gas keep temperatures high. Here, any volatile ices, water, carbon dioxide, carbon monoxide, ammonia, are quickly vaporized. Only the most refractory solids can exist as dust, metallic grains and silicate minerals, the raw ingredients of rocky planets. As you move outward, the disk cools. At larger distances, temperatures drop enough for various gases to condense as solid ices on the surfaces of dust grains. Water molecules begin to freeze out, coating rocky particles in icy mantles. Even farther out, more volatile species like carbon monoxide and methane can also freeze. The result is a chemically stratified disk, an inner rocky zone with mostly bare silicate grains, and outer regions where grains are a mixture of rock and ice. This simple temperature gradient has profound consequences. In the inner disk, there is relatively little solid material per unit volume because only refractory dust survives. In the cooler outer disk, ice dramatically increases the solid mass available. Larger, stickier icy grains collide and clump more efficiently than small, bare, rocky dust. The seeds of giant planets and icy small bodies, future comets and Kuiper belt objects, are planted in these cold regions. Among the many transitions in the disk, one is especially important: the water snow line. The snow line is the distance from the young sun where temperatures fall low enough for water vapor in the disk to condense into solid ice on dust grains. It is not an infinitely thin boundary, but a radial zone where the dominant phase of water shifts from gas to solid. In classical models of the early solar system, the water snow line lies roughly around 2 to 3 astronomical units from the sun, between the orbits of Mars and Jupiter, though its exact position moved over time as the disk cooled and evolved. Inside this region, water remains mostly as vapor, and solid particles are composed mainly of silicate rock and metal. Beyond it, dust grains become ice-rich, incorporating frozen water and other volatiles. This transition matters because ice adds mass. Beyond the snow line, the amount of solid material available to build objects increases significantly. Icy grains are not only more massive, they are also more efficient at sticking together during collisions. This allows planetary cores to grow more rapidly. In the outer disk, large, icy planetesimals and protoplanets can form fast enough to capture substantial envelopes of hydrogen and helium before the gas disk dissipates, forming gas giants like Jupiter and Saturn. In contrast, inside the snow line, where solids are limited to rock and metal, planet embryos tend to remain smaller and become terrestrial planets. We now observe snow lines in protoplanetary disks around other stars with instruments like ALMA. These observations often reveal rings and gaps at distances matching the expected condensation radii of different ices, reinforcing the idea that snow lines are active sculptors of planetary systems. The snow line is not just a temperature marker, It is a structural boundary that helps set the overall architecture of a planetary system. Inside the snowline, inner disks tend to produce compact, rocky worlds, planets like Mercury, Venus, Earth, and Mars. In this region, there is less solid material available, and growth is slower. Planetary embryos reach sizes of Earth or smaller and do not typically acquire thick atmospheres of hydrogen and helium. Beyond the snowline, the story changes. The greater abundance of icy solids allows planetary cores to assemble quickly, reaching tens of Earth masses in relatively short timescales. These massive cores can then gravitationally capture large envelopes of gas from the surrounding disk, forming gas giants and ice giants. Even bodies that never become full-fledged planets, like many Kuiper Belt objects, retain their icy composition, preserving a record of the cold outer disk. The presence and movement of snowlines over time can also influence where belts of small bodies form. Regions just inside and just beyond the snowline can become filled with leftover planetesimals, asteroids and comets that never merged into planets. In our solar system, the main asteroid belt, the giant planets, and the icy Kuiper Belt all carry the imprint of this early thermochemical structure. By the end of this section, the viewer should feel the snowline as a kind of invisible frontier, a moving, temperature-driven border that decides which parts of a planetary system will be dominated by rock and which will be rich in ice, and therefore which regions are likely to birth giants, icy worlds, and reservoirs of small frozen bodies. Before there were asteroids, moons, or planets, there was dust, unimaginably fine dust, smaller than smoke particles. Inside the protoplanetary disk around the young sun, these dust grains were mostly silicates and metals in the inner regions, and silicates plus ices beyond the snowline. Their sizes ranged from fractions of a micron to a few microns, comparable to particles in cigarette smoke or volcanic ash. In that environment, there were no gentle hands to press them together, only physics. Dust grains moved through the gas, bumping into each other at low speeds. When two particles collided, electrostatic forces, tiny charges on their surfaces, helped them stick rather than bounce apart. Over time, repeated collisions built up loose, fluffy aggregates, open, snowflake-like clumps of many grains bound together. These dust snowballs could grow from microns to millimeters, and then to centimeter-sized pebbles. The disk was full of these aggregates, each one a tiny step toward something larger. At this stage, growth is relatively easy. Low-speed impacts, sticky surfaces, and abundant material all favor assembly. But this gentle phase of dust coagulation cannot continue forever. Once particles become large enough, new barriers appear. As dust aggregates grow into pebbles and boulders, roughly from centimeters to meters in size, they begin to interact differently with the gas. The gas in the disk orbits the young sun slightly more slowly than Keplerian speed, because gas pressure partially supports it against gravity. Solid particles, however, try to orbit at the faster Keplerian velocity. This mismatch creates a headwind. Larger solids feel drag as they move through the slower gas. That drag robs them of angular momentum and causes them to spiral inward toward the sun. The timescale for this inward drift becomes very short for meter-scale bodies in typical disk conditions. In some models, they can fall into the star in just a few hundred or thousand years. At the same time, collisions between such larger bodies become more violent. Instead of gently sticking, impacts at higher relative speeds can fragment or erode them. This creates the so-called meter-size barrier. Simple growth by sticking is no longer efficient, and objects risk being ground down or lost into the sun before they can become planetesimals, hundreds of meters or kilometers across. This is one of the central puzzles in planet formation. How do solids cross this dangerous size range without being destroyed or swallowed by the star? Modern models suggest that planetesimals did not grow only by slow, pairwise sticking. Instead, entire swarms of pebbles may have collapsed together under their collective gravity. One key mechanism is called the streaming instability. In the streaming instability, dust and pebbles interact with the surrounding gas in a way that causes them to clump. Regions with slightly higher particle concentrations slow the gas more strongly, which in turn causes more solids to pile up there. This feedback creates dense filaments and clumps of solids embedded in the gas. Instead of being evenly mixed, the disk develops pockets where the local density of rock and ice is dramatically enhanced. If these concentrations become dense enough, the solid's own gravity can take over. In such regions, pebbles no longer behave like independent grains. They act like a collective fluid that can undergo gravitational collapse. Within a relatively short time, these dense filaments can break up into self-gravitating clumps that contract into kilometer-scale planetesimals without passing slowly through every intermediate size. This picture solves part of the meter-size problem. Instead of each rock trying to survive the dangerous drift regime alone, pebbles gather into gravitationally bound groups and jump directly to planetesimal sizes through collective collapse. The outcome of this collapse phase is the birth of planetesimals, solid bodies ranging from a few kilometers to hundreds of kilometers in diameter. Unlike fluffy dust aggregates, planetesimals have enough self-gravity to hold themselves together as coherent objects. Their interiors can be a mixture of rock, metal, and ice depending on where in the disk they form. These are the first real building blocks of planets. Planetesimals are massive enough to gravitationally perturb each other, to stir their surroundings, and to accrete smaller particles and other planetesimals. Some may differentiate internally, with heavy elements sinking to form metallic cores and lighter materials forming mantles and crusts. Others remain more primitive, preserving the original mixture of materials from their birth region. But this stage is anything but peaceful. As planetesimals orbit the Sun, they collide with one another. Some encounters are gentle enough to merge two bodies into a larger one. Others are catastrophic, shattering objects into fragments and returning material to the smaller size population. Growth and destruction happen side by side. Over millions of years, a complex collisional cascade shapes which objects survive and which are reduced to dust. As time passes, gravity rewards the winners. In the inner solar system, where orbital periods are short and densities are higher, planetesimals collide frequently. A few bodies grow larger than their neighbors and begin to dominate their local zones. Through continued accretion, these embryos evolve into protoplanets, objects with masses comparable to the Moon or Mars. Their gravity clears nearby orbits, sweeping up remaining planetesimals or flinging them away. Ultimately, a small number of these embryos merge in giant collisions to form the terrestrial planets: Mercury, Venus, Earth, and Mars. In the outer solar system, the story is shaped by both growth and disruption. Beyond the snow line, there is more solid material, so massive cores can form more rapidly. Some of these cores become the seeds of gas giants, capturing enormous envelopes of hydrogen and helium. Others remain as icy dwarf planets. But here, the gravity of the growing giants also acts like a celestial slingshot. Many planetesimals are scattered outward into distant, elongated orbits, forming populations like the Kuiper Belt, and even farther, the Oort cloud. Some are sent inward, where they may collide with the inner planets or be accreted by the Sun. Most planetesimals never reach planetary status. Instead, they survive as asteroids, comets, and small icy bodies, fossils of an era when collisions and gravity were rewriting the architecture of the young solar system. The small bodies we observe today are the survivors of a long and violent selection process. They represent the fraction that was not absorbed, shattered beyond recognition, or ejected into interstellar space. By the end of the main building phase, planetesimals are no longer evenly distributed. Gravitational interactions with forming planets sculpt them into distinct reservoirs. In the region between Mars and Jupiter, the strong gravity of Jupiter prevents a single planet from forming. Instead, collisions and resonances keep many bodies from merging into one large world, leaving behind a broad belt of leftover rocky planetesimals, the asteroid belt. Farther out, beyond Neptune, a wide population of icy planetesimals remains in a flattened ring called the Kuiper Belt. Some of these are dwarf planets like Pluto and Eris. Others are smaller, more primitive bodies. Beyond that, on scales thousands of times larger than Earth's orbit, a vast spherical cloud of icy planetesimals, the Oort cloud, is thought to surround the solar system, populated by objects that were scattered outward during the formative years. So when we look at asteroids and comets today, we are not seeing random debris. We are seeing the remnants of a planetary construction site, concentrated in regions where gravity and orbital dynamics allowed them to survive. They are the building blocks that never fully assembled into planets, preserved at the edges and gaps of the solar system's architecture. In the quiet gulf between the orbits of Mars and Jupiter, there should have been another planet. The young solar system had more than enough raw material: rock, metal, and ice swirling in the protoplanetary disk. Instead, we find a vast, delicate swarm of bodies, from microscopic dust grains to dwarf planet-sized cirrus, spread across a region roughly between 2 and 3.5 astronomical units from the Sun. This is the asteroid belt, the fossilized remnant of a world that failed to assemble. The main culprit is Jupiter. As the largest planet grew, its enormous gravity began to tug rhythmically on the orbits of the planetesimals in this zone. Each time a small body orbited the Sun, an exact, simple fraction of Jupiter's orbital period, say 1 to 2 or 3 to 1, it felt a regular gravitational kick. Over millions of years, these orbital resonances pumped up their eccentricities, turning nearly circular paths into elongated crossing orbits. Instead of gently colliding and merging into larger objects, the planetesimals increasingly smashed into one another at high speeds, fracturing rather than growing. The result is a population of rocky bodies that never made it past the audition phase of planetary formation. We see the fingerprints of Jupiter's interference in the structure of the belt itself. Gaps at specific distances, known as Kirkwood gaps, mark the locations of strongest resonances, where objects have been cleared out or violently stirred over the age of the solar system. The total mass that remains today is tiny, only a few % of the Moon's mass, a thin, gravitationally scarred relic of what might have become a fully fledged terrestrial planet. Far beyond the orbit of Neptune, the Sun's light becomes weak and blue, and temperatures plunge so low that water, methane, carbon monoxide, and carbon dioxide all freeze into solid ice. In this realm, roughly from 30 to beyond 50 astronomical units, lies the Kuiper Belt, an enormous ring of icy planetesimals, the outer sibling of the asteroid belt. Kuiper Belt objects are mixtures of rock and volatile ices. Some are small, irregular bodies only a few kilometers across. Others are large, complex worlds like Pluto, Eris, Makemake, and Haumea. Dwarf planets with thin atmospheres, layered interiors, and even moons. This region preserves material that has been only lightly processed since the early days of the solar system. In many ways, each Kuiper Belt object is a time capsule, preserving the chemistry and temperature conditions that existed where it formed. Yet, just like the asteroid belt, the Kuiper Belt also tells a story of disruption. Early in solar system history, the giant planets did not sit exactly where they do today. As Jupiter and Saturn interacted gravitationally with the surrounding planetesimals, they migrated slightly. Neptune, in particular, likely moved outward. In doing so, it scattered and reshaped the population of icy bodies beyond its orbit, stretching their paths and trapping many into resonances, such as the 3 to 2 resonance that captures Pluto and similar objects. The Kuiper Belt is not a quiet, undisturbed ring, but a dynamically sculpted structure, its present architecture a frozen trace of the giant planet's migration. If we keep traveling outward, long past the Kuiper Belt, the Sun eventually shrinks to a bright star among many. At these distances, thousands to tens of thousands of astronomical units, the solar system transitions into interstellar space. But even here, theory predicts that the Sun is not alone. Surrounding our system like a vast, fragile bubble is the Oort cloud, a spherical reservoir of icy bodies that extends perhaps up to 100,000 astronomical units, nearly halfway to the nearest stars. We have never seen the Oort cloud directly. Its objects are too small, too distant, and too faint to detect. Instead, we infer its existence from the behavior of long-period comets. those that dive into the inner solar system on highly elongated, randomly inclined orbits that can take hundreds of thousands or even millions of years to complete. The simplest explanation is that these comets spend almost all their lives in a distant, roughly spherical distribution of bodies, occasionally nudged inward by passing stars or the tidal pull of the Milky Way's gravity. The origin of this cloud traces back to the chaotic youth of the giant planets. As Jupiter, Saturn, Uranus, and Neptune formed and grew, they scattered nearby icy planetesimals in all directions. Some were ejected entirely from the solar system, becoming interstellar wanderers. Others were not quite fast enough to escape and instead were flung into extremely distant bound orbits. Over time, the combined gravitational tug of the galaxy and nearby stars randomized those orbits into an enormous, diffuse halo. The Oort cloud, if it exists as predicted, is the most remote component of our planetary system, a nearly invisible archive of bodies that were born near the giant planets and then exiled to the frontier. When gravity disturbs one of these distant bodies, from the Kuiper belt or the Oort cloud, its path can change dramatically. Some are nudged onto orbits that bring them into the inner solar system, where sunlight warms their surfaces, ices begin to sublimate, and a coma and tail blossom around a previously invisible nucleus. These comets are not random visitors. They are emissaries from specific reservoirs. Short-period comets, with orbits of a few years to a couple of centuries, mostly originate in the Kuiper belt and the related scattered disk. Their paths tend to stay close to the plane of the planets, suggesting a source in the flattened, disk-like population beyond Neptune. Long-period comets, whose orbital periods can stretch into tens or hundreds of thousands of years, arrive from all directions in the sky, consistent with a nearly spherical Oort cloud. Each time such a comet appears, it offers a rare sample of material from the farthest reaches of our system. Ices and dust largely unchanged since the earliest phases of planet formation. In that sense, asteroids, Kuiper belt objects, and Oort cloud comets are more than minor characters in the story of the solar system. They are the small, stubborn survivors of a violent competitive formation process, the leftover bricks and fragments from which planets were built. By studying them up close with spacecraft and from afar with telescopes, we are effectively drilling cores into the first few million years of our system's history. The small bodies are, in reality, the oldest witnesses we have. Asteroids and comets are not just leftovers. We can think of them as physical time capsules from the very beginning of the solar system. Unlike full-sized planets, most small bodies never went through global melting, tectonics, or long-term volcanism. They did not erase their past with oceans, atmospheres, and plate motion the way Earth did. Their interiors remained relatively cold and simple. That means their chemistry, their minerals, and even the tiny trapped grains inside them are still very close to the original material of the protoplanetary disk from 4.5 billion years ago. When we study them, we are not looking at a copy of the early solar system. We are looking at the original record. Some asteroids occasionally send fragments toward Earth. When those fragments survive atmospheric entry, they land as meteorites. A specific class of meteorites, called carbonaceous chondrites, is especially valuable to science. They are chemically primitive. Their overall composition is very close to that of the original solar nebula, minus the lightest gases. Inside these meteorites we find chondrules, tiny, once molten droplets of rock that cooled quickly in the early disk. Calcium-aluminum-rich inclusions, CAIs, some of the oldest solid materials ever formed in the solar system. Fine-grained matrix, a dark, dusty material that still preserves unaltered interstellar and nebular grains. Because these rocks never fully melted into separate core, mantle, and crust, their chemical record was never reset. Their mineral mix and element ratios tell us about temperatures, pressures, and radiation in the protoplanetary disk long before Earth existed as a planet. When we analyze certain asteroids and comets, we find minerals that could only have formed in the presence of liquid water, hydrated silicates, clays, carbonates. In some meteorites, these water-related minerals are mixed with complex carbon-based compounds, simple organics like amino acid precursors and more complex organic matter. These findings tell us two key things. Early small bodies were not completely dry. Some of them briefly hosted liquid water in their interiors, as radioactive elements warmed the rock and ice. Organic chemistry was already active in these environments, long before life appeared on Earth. By comparing the isotopic fingerprints of hydrogen and oxygen in meteorites and comets with those in Earth's oceans, scientists can test how much of our planet's water might have been delivered by impacts from these primitive bodies. Small bodies are not just fossils of rock and ice. They are records of how water and organic molecules were distributed throughout the young solar system. If you could hold a fragment of an asteroid or comet in your hand, you would be touching solid material that formed before any mountain range on Earth, before any ocean, before the first living cell. The rocks beneath our feet have been recycled many times by plate tectonics, erosion, and volcanism. But the interiors of many small bodies have remained almost unchanged since the first few million years after the Sun was born. That is why missions that collect samples from asteroids and comets are so powerful. They are not just bringing back space rocks. They are bringing back pages from the original chapter of the solar system's story, pages that were never rewritten. In that sense, we often focus on planets because they are large and visually dramatic. But the true archive of how our system began is written in small letters, in dust, in stone, in buried ice. The asteroids and comets we study today are the quiet archivists of cosmic history, patiently carrying the memory of a time when no planets yet existed, and the solar system was only a swirling disk of gas and grains.